In this video, I will present how to approach physics problems where an object is on a ramp. There are a couple of little tweaks that we make to our thinking that can make these problems quite a bit easier. So we have a problem where we have a person pushing a heavy frictionless cart. We know the mass of the cart is 97.2 kilograms up a 22.5 degree incline. With what amount of force must the person push the cart to move it at constant velocity? So constant velocity is key. That would be zero acceleration. We need to draw a force diagram where forces are balanced. So first of all, let's just note the 22.5 degree incline. That will be, in the diagram, this angle right here, 22.5 degrees. So when I draw my force diagram, one important tip that will help you is to tilt your force diagram. So essentially, what we want to do is take the x-axis, and instead of making the x-axis horizontal like we normally would, we're going to make the x-axis be parallel with the ramp surface, something like that. That means the y-axis will be tilted as well, 90 degrees away. So something like that. And the best you can, try to make it accurate so that this does look like a 90-degree angle in your force diagram. So things don't get too messy, I'm going to actually draw my force diagram over here on the right. So again, I'm going to try to draw my x-axis so that it is tilted the same amount as the ramp. Something like that. And again, I want to, as best I can, make this a 90-degree angle here for the y-axis. That's not the best, but we'll make it work. So here's my y-axis. Here is my x-axis. Now, starting the force diagram, we know, and we've done this many, many times, that we want to draw in the force of gravity on the object. So that will always be straight downward. And again, when you're doing this by hand, you want to make sure that this vector is straight downward on your paper. So I'm going to draw it as best I can, straight to the bottom of the screen. And that will be Fg, the pull of gravity on the object, which we know we can take the mass in kilograms times g to get that value. So 97.2 kilograms times 9.80 newtons per kilogram gives us a weight of 953 newtons. Okay, that is the pull of gravity on this object. So what we do here is notice that that gravitational vector no longer falls along the x-axis. It's actually in its kind of own direction, and it is a vector of which we would want to find the components. So again, this is a case where we want to be careful in how we draw this. I'm going to go ahead and sketch out my guidelines for this vector. Now everything needs to be tilted, right? So my guidelines are also tilted, something like this. And again, I'm trying to draw my guidelines so that this is a 90-degree angle here and here. So let me go back in blue and draw in the two components to gravity. I'm going to be careful in the length that I draw them. So that is the component of gravity that acts down the ramp. I'm going to call that Fgx. So the x component of gravity. There's a component of gravity that's also pulling the cart into the ramp, and it's going to be this long. That is Fgy. Okay. And what else is acting on the cart? Well, the person is pushing up the ramp and they want to push it at constant speed. So I'm going to draw the push as if it originates at the object and goes up the ramp. And I'm going to draw it roughly the same length as FGX. So this is going to be F push. And if I'm moving this at constant speed, I can assume that those two forces are equal in magnitude. Otherwise, the cart would be accelerating. If I didn't push it hard enough, the acceleration would be down the ramp. If I pushed it bigger, with a bigger force, I would be accelerating it up the ramp. And if I just took away my push, it would accelerate down the ramp because we would have an unbalanced FGX. Now, one of the tricky parts of this is there is another force. So gravity is pulling this cart into the surface. And when we first learned about normal force, we said that normal force is always perpendicular to a surface. So although gravity acts downward, normal force is going to be perpendicular to the surface. So the normal force vector is actually going to fall along my tilted y-axis. And as you might guess, if there's no acceleration away from the ramp or into the ramp, that normal force vector should be congruent with FGY. So I'm going to try to draw that as best as I can upward along that tilted y-axis, trying to draw it the same length. That's going to be our normal force. I know that that will be congruent to FGY. This particular problem does not ask you to solve for normal force, but if I did want to solve for normal force, if I can find FGY, I will have also found the value of normal force. So summarizing here, the magnitude of normal force should be equal to the magnitude of FGY, and the magnitude of the push should be equal to the magnitude of FGX, the x component of gravity. So that's what this problem is asking for. What amount of force must we push with to move it with constant velocity? So another little tricky aspect of this problem is the angle, the 22.5 degrees in the ramp. That's not directly shown in the diagram, but I want to show you how you might figure out where that 22.5 degrees comes into play. So let me do this in another color. I'll do it in green. And this is not part of the force diagram. Once I'm done with this piece, I'll go ahead and erase the lines that I'm going to draw next. So I do know, because of the way I've tilted my axis, that if I drew in a horizontal line here, that the 22.5 degrees would be that angle right here, okay? I also know, if I've drawn this properly, if this green line is horizontal and gravity is straight down on the page, that this would be a 90-degree angle, okay? So I've made a right triangle. Again, this is not really part of the force diagram. It's just an argument to figure out where our angles lie. If this is 22.5 degrees and this is a right angle, then this would have to be 90 minus 22.5 degrees. In other words, this angle here is 67.5 degrees, because those two angles would have to add up to 90. By the same argument, if this whole angle here is 90 degrees and this is 67.5, the rest over here should be also 22.5 degrees, okay? So that's a way that I can start to work out FGX, is if I know one of these angles. So I'm going to go ahead and remove all the green lines, keeping in mind where the 22.5 degrees is. This angle here would be 22.5 degrees. And this angle here is 67.5 degrees. And I'm trying to find FGX. So I can really work with either one of those angles. I'm going to go ahead and work with the 67.5 because I'm trying to find the adjacent side, FGX, compared to the hypotenuse, which I know. So I'm going to go ahead and write cosine of 67.5 degrees would equal the adjacent side, FGX, and I'm working with magnitudes here, over the hypotenuse, which is the full strength of gravity, pull of gravity on the object. That's 953 newtons. So to find the magnitude of FGX, I'm going to multiply both sides by 953 newtons. That will cancel. 953 newtons times the cosine of 67.5 degrees happens to equal 365 newtons. That is the magnitude of FGX. From my force diagram, I also know that that's equal to the magnitude of my push. And that is what I'm looking for in this problem. Now again, it doesn't ask me to find the normal force, but I could do that working with these angles and my right triangles here. I won't work through that in this example, but that is a good cue to end the video. Good luck with ramp problems.